Okay. So I won't be able to see the chat because of my monitor setup. So if you got any questions, please feel free to interrupt. So let's get going. So I'm going to be talking about the Bevy ECS, particularly version 0.1, 0.11. Now, Bevy is in a little bit of flux at the moment. It keeps changing its APIs. And if you looked at the APIs that I'm going to talk about, just even a couple of versions ago, it'll be quite different. So who knows, maybe in version 12, all of this will be out of date. So who am I? I'm Matt Davies. I've spent roughly 27 years in the video game industry. I'm a senior engineer for a company called Rocket Science. We do a lot of code dev in the video game industry. And I specialize in engine design and code architecture. That's pretty much my background. And you can reach me on badcode@pm.me. That's a 0, not an O there. So what this talk is going to be about, I'm going to explain what ECS is, and I'm going to explain Bevy's implementation with the specific crate called Bevy_ECS. This is part of the Bevy engine. In fact, when you bring in the Bevy crate, it will pull this in. But I think it's important to understand this particular crate because you can use it in other applications and software. You don't have to use it in the Bevy engine because it's quite standalone. And I'm going to do some live code examples. So hopefully the demo gods are with me. What this talk is not about is not a talk about the Bevy engine in general. I won't be covering Bevy app crate. I did plan to do that, but this talk will be just about the Bevy ECS because as I was writing the designing the talk, I realized it's just too much stuff to talk about to fit in roughly about an hour. And I'm not going to be talking about how to implement your own ECS. Implementing your own ECS is quite involved, and there are better videos out there to explain how that works. So before ECS existed, during the 90s, when we wrote games, because we were programmed in C++, the game design, the handling of objects within the game was very object-oriented. And this caused problem with hierarchies, the object hierarchies, particularly when I added a new object to my system, which other object do I derive from? So this ended up in a very non-scalable kind of architecture. For example, you can imagine a game that has a character-based class, then we derive a bad guy base class and a friendly NPC, and then we decide to add an evil wizard, which we think, okay, that's derived from bad guy. Evil wizard particularly handles all the spell casting, perhaps, and then the game designer comes up to you and says, okay, but I want a friendly wizard. But so that seems that we need to derive that from friendly NPCs, so it may have a conversational functionality, but we really need the spell casting functionality from the evil wizard. So then we have to refactor the object hierarchy and maybe even enter multiple inheritance. It was quite painful. So it soon became very apparent to the industry that we needed to prefer composition over inheritance. It was kind of obvious, so much obvious that I independently invented a system for a video game called The Thing 2, which never came out, called behaviors, which essentially you had game objects and you added behaviors, but the behaviors contained code and the data that went along with that behavior. So essentially each behavior in the system was ticked. And Unity and Unreal has a very similar kind of system. Unity has game objects where your mono behavior is ticked, and Unreal has actors and components. But it still has problems. It's slow at huge numbers of game objects, and it still mixes code and data. Code and data decoupling is quite important because that allows you to reinterpret data from a different point of view. And like a tree, for example, could look different to to a human than to an ant, but it still is still a tree. So eventually the ECS solution was proposed. I can't tell you exactly where it came from, but it suddenly became very popular within the video game industry, and it promises that it's much faster and much more cache friendly. The code and data are decoupled, and then essentially your code operates over many entities rather than just a single one. And when you had game objects and attached behaviors, essentially that behavior only saw the object it was in. Now the code in the ECS looks at many entities and can make decisions based on multiple objects rather than have that myopic view of a single object. It has composition, and as you will see, it is automatically parallelizable as well, which basically means that you automatically take advantage of all the CPU cores you may have. And Bevy makes extra promises that it's really easy to use. Unlike Unity Dots, which is a little bit more complicated, and Unreal Mass, which I like to call Unreal Mess because it's just a terrible system. So what is ECS? ECS just stands for Entities, Components, and Systems. As simple as that. So entities, they're just containers. They contain all components it requires. So an entity can represent any sort of game, object, or concept, whatever you need it to be. For example, a player, a gun, an inventory, UI. It essentially just represents a thing. And the characteristics of that thing is defined by the components that you add to the entities. So, for example, we could have a player entity and a door entity in this example. So components, they contain only data as a series of fields. They're stored efficiently. This allows for the cache-friendly aspect of ECS, and allows and helps with scaling to hundreds of thousands, whatever you need, objects. They're essentially attached to an entity, but each entity can only have one instance of a type of component. So if there's a component that represents health, you can only have one health component within each entity. So, for example, in our player and door example, a player can have position, velocity, health, and inventory components. The door can have position, health, and door state. You notice that both the position and health are reused in both entities. That's perfectly fine, because components, because code and data are decoupled, the data on various entities can be handled in different ways. Systems is just the code that acts on a list of components. Each system queries all the entities that could turn a certain combination of components. For example, a system could say, give me all the entities that have both position and velocity components. And the system can write and read to and from the fields in those components. And on top of that, it can also query which entities, as in the ID, that each collection of components belong to. For example, you could ask for all the entities that have both velocity and position components, and also along with that, you can have the actual IDs for each of the entities that contain those components. So this is essentially the stuff that acts on your entities. So what is Bevy ECS specifically? Every ECS system has their own kind of implementation and quirks and stuff. You got in C++, you got ENTT or entity. Unreal's got mass. Unity's got dots, and there's various ECS implementations out there. But we're talking just about Bevy ECS right here. So what does Bevy ECS have? It has all the above that I've just described as the basic characteristics of an ECS system. But on top of that, the components are just Rust structures, and systems are just Rust functions. This makes Bevy's ECS one of the most ergonomic ECS systems out there. If you compare that to Unreal's mass system, where all the components and systems are actual whole C++ classes, the ergonomics is just night and day. On top of that, we have some supporting players, some other concepts that I'm going to talk about that go along with ECS. we have a world, a schedule, resources, command list, component bundles, and system sets. And I will talk about these. So the first concept is the world. The world's role is to contain all the data and resources used in the ECS. Essentially, it collects all the entities and the components. It owns them. It owns resources. I will talk about that another time. And it owns in Bevy events. I won't be talking about events because the events, even though they are supported within the Bevy ECS crate, they really are the mechanism to using them exists in the Bevy app. So if I give a part 2 talk to this, which I intend to do, I will go over events then. So here we have in the world creation. So let's go to my VS Code and let's start writing some code. So the first thing we need to do is to go to cargo toml and let's bring in Bevy 0.11. Then I've got Bacon running here. So if I'm going to add in, let's see now, let world equal world new. That will create me a blank world. Have a look at this. We'll just compile Bevy ECS for the first time. You shouldn't have to compile again. We could use Bevy ECS prelude to bring everything in. Oh, I just realized I should have done Bevy ECS here. The demo goes already against me. That's much better. I'm compiling a lot less code. Okay, and just for the purpose of giving these warnings, I'm going to add a directive here. Okay, so we got an empty world now. Great. So the world contains entities. So we can create a blank entity. Let's say we create a player 1. We can do that using just the world spawn empty. And we need to make the world mutable. And that's essentially how you do that. But entities can also contain components. So we can add components easily enough to the entity. So this play 1 is just an ID. It's a type entity mute. And on there we can say we'll add a couple of components. So components in Bevy are just simple structures, but they need to be derived with the component trait. And we'll create another one. And we can add these easily here. Player one, insert. To insert multiple components, we can just use a tuple of those components. So let's take the X and Y and Z values so they're a bit more interesting. In fact, let's get rid of these Z values. We don't need 3D for these demo purposes. Okay, what's happening here? Oh, player one has to be mutable. Okay, so here we've just created a player entity by creating spawning an empty entity and then adding components to it. I can also do exactly the same in one go by just using the world spawn function, which does exactly the same thing. So that's created a world with two entities, and both entities have two components. So the next thing, the next concept that Bevy adds to Bevy ECS create is a schedule. And a schedule ensures that all systems execute. It handles things called run conditions, which I'll talk about later. Run conditions allow you to conditionally run or not run a system. It manages command lists. Command lists are a way of changing the state of the world from within a system. It manages system ordering, so that determines, which order the systems run. Do they have dependencies? Can they be run at the same time, and so forth. It also manages change detection, so you can run systems based on aspects of your entity component hierarchy changing or being created or being removed. And it also manages a constant cost system test, which I'll also talk about later. So here we have a schedule, and this is a separate object that sits beside the world. So in Rust code, it will be that. But schedule owns the systems. So when you run these systems, you apply a world to that schedule run, and so therefore you can, if you want to, have the same schedule with the same systems operate on different worlds of different types, if that's your thing. So what is actually a system? How do we really write a system in Bevy? So system, it must be a function that comprises of system parameters. That means that the parameters you pass to the function must be of a particular type. So if you don't have if every single parameter that you pass into a system function isn't of one of these types, then it cannot be accepted as a system and it cannot be added to your schedule. There are various system parameter types that I want to talk about. There is one type is a query type, and the query types allow you to say, okay, give me all the entities with these components, and you can do various filters on that, which I'll talk about later. Another system parameter could be access to a resource. Another is access to the commands list, so you can mutate the world from within the system. You can have system parameters that handle events, so either the event writer or the event reader. The event writer will broadcast events to any system that has the event reader of that type, and so that way you can broadcast messages across systems. This is how systems will usually communicate between each other. And you have local storage as well, where a system has its own local storage that it maintains on a per system basis. And I'm going to show how I would write a system right now. So I'm going to write a function called show things. And I'm going to take the query, and it's of a query type. And I want to show all the entities that have a position and just have a position. So I can just do that. And let's look at what that system is doing. It's taking a query where I say I want all the entities that have a position component. This reference to query can be transformed into an iterator, and we're looping through that iterator. And so every single component, every position component within all the entities gets passed a position. Here we can just print them out. So we hope that let's but we need to add it to our schedule. So we do that by adding a systems call, and we can just say add show things. This needs to be mutable, and to actually get things running, we call run, and we have to pass in a reference to the world that we're going to run on. So if we look at the output, we can see that the system's being run, and it's looping around two times because there's two entities that have a position. Great. So queries. Queries, as I showed you just now, provides an iterator over all the entities that contain a collection of components. Now all components that need to be read or written to are provided in a tuple, the generic parameter. And I'm going to show what I mean by this. For example, if I wanted to show things, but I want to include velocity, I can't just do that. That would be an error, I think. Or is it allowing me to do it? Oh, interesting. But usually you need to put it in a tuple like this. So in the loop, I can destructure it here, and I can then add maybe the velocity here. Okay. So now we can show the velocity here. But we can also filter on just the existence of components. We may be not interested in reading or writing to that component, but we just want to only include entities that have this extra component, so we can separate similar components. An example of this is if I added a new component here called a player component. And I'm not going to have any field in this. So this is what we call a marker component. And we can add a player instance to each of our players. And maybe we want to have a query that shows all the positions that have a player. And we do this by passing the with player inside the query. What's going on here? So, for example, player at position this, and yeah, what's going on here?
Do you just need a capital P in position there?
Oh, yes, I do. Yep, I do. Yeah, it's a type. And what's going on? Oh, I forgot the there you go. And maybe we'll add another one saying show monsters, assuming that if it's not a player, it's a monster. We can do a very similar thing using without player. So let's add some monsters too. Let's let monster equal world spawn. There you go. And not having the player component, we're saying this is a monster. And then we need to add this to our schedule. So we can do this by single call add systems. And we can put these systems in a tuple like so. And this should print out thing, player, monster. Now, as I run this, you can see that things appear in different orders all the time and sometimes interleaved. This is because all these systems are being run in separate threads. This is able to happen because we're reading from the components, and so therefore it is safe that all these systems run at the same time. Now we can write to components, and I will show how you can possibly do that. For say every time we show the monster, we want to change its position. We can, if we wanted to, mute the query, have a mutable reference to position, and from that we could just do position dot x plus equals 1, for example, and this needs to be mutable as well. What's going on here? Oh, we need to make that mutable, and that is fine. You can do that. So when this system runs, it will change that component at the end of it. But we don't want to do that right now. I just wanted to demonstrate what you would do for mutating components. Right, but we can do more. We can filter on only on components that have changed. I'll show some examples about that later. That's called change detection. But as I was talking about, the access patterns of all these components can determine how systems can run concurrently. So in our example, we just read only at the moment. So all of the systems can run at the same time on separate threads. So, but we can, if we cared, we can do system ordering. This allows us to make sure that a system runs before another system or after another system. So systems can be marked as required to run before or after another system by using the dot after and dot before methods on actual system function call. So for example, I could, if I wanted to here, say I wanted the monsters to go before show things. And just by adding that, you can see that monster will always go before thing, no matter how many times I run it. And I can do something similar with after. Again, monster will run always after the thing. Let's say we wanted all these 3 systems to run in a row in that order. So we don't want show things, show players, and show monsters to run concurrently. We want them to run in sequence. There's a much easier, rather than doing show things before show players before show monsters, we can just add dot chain on the tuple. And this will make sure that things, players, and monsters will always be that order, no matter how many times you run it. You could also assign labels. Actually, I'm not sure if we can do that anymore. That might be an old Bevy thing, so I'll have to look into that. But later on, I'll talk about system sets, which allow you to apply after, put sets in a grouping and apply after and before to those groupings, which helps manage the complexity of dependencies between systems. So resources is another concept that you want to know in Bevy. So essentially, resources are global variables within the world. Systems can read to them via the res type as a system parameter, and it can read and write to them via the res mute type. So essentially, the model you want to have is that in the world, we have the entities and components, but we also contains the resources. And these resources can be accessed via systems using those system parameter types. So for example, I want to move my creatures, whether they're monsters or players, by applying the velocity to a position, but I kind of need a game time. And for now, I'm going to have the game time as a resource. We do that by driving resource rate, and I can just do game time F32. So now we will need to add that to our world, and we do that by doing world insert resource, and I can just create a value right there. Let's say 0.1. And so now there's this global resource which of type game time. Now, it is important to note that resources are named by the type. There's no labels with resources, so you only have a single game time resource. Rust makes it easy by having a wrapper structure around something, so you can have it's the new type paradigm that's often used in Rust. So now we want to move the players. So we'll create a system, move creatures. And we want to query on the position which we want to mutate. That has to be mutatable as well. And then we want to bring in the velocity. But then we want to bring in the game time, which is res game time. And we just loop through the query, get in the position, the velocity, and apply in the velocity times the game time. We want to add the system to the schedule, but we kind of want to make it move before the actual all these shows things happen. So we can put this tuple in another tuple, and we can add move creatures, and we want it to be before show things and before show players and before show monsters. Okay, so we've got the show things here in the J. Oh, get rid of that. Now this before is quite messy, but as I said previously, we have a concept called sets that allow us to make this a little bit easy. And now we'll refactor this code later. But for now, we're basically saying we want the move creatures to run concurrently with everything else except that we want to before all the show stuff. So what's going on here?
I think it's again not a tuple.
Oh, tuple, yep. Thank you. There we go. And here we go. So here we notice that all the values they've basically moved by 0.1. Okay. So commands list. Commands list provides a very similar API to the world and schedule for manipulating entities, components, and systems. This means that you can spawn entities, you can add components, you can insert systems in exactly the way you would do with the world and the schedule objects. But you can do this within a system. However, there's a constraint. You can't just change the state of the world at any time you wanted to, because you'll have race conditions, and Rust won't let you do that anyway. So what happens is when we add these operations to mutate the world and schedule onto the commands list, and the commands list will get processed at the end of this current scheduled run after all the other systems have executed. So, for example, if I wanted to, I could, just for giggles, I can create another player whenever the creatures move. So bring in commands, which is mutable. And we can say commands spawn another player. So let's run this. As you can see, even though we move before we show, we still only have 2 players. This is because by the time that the show systems have executed, we still haven't mutated the world. So to show that it does actually happen at the end of the schedule, we can just simply run the schedule twice. And when that happens, you can see now there's 3 players there. Okay. Let's get rid of this. Okay. The next thing I want to talk about is local storage. Now, local storage allows you to just store values that is only local and specific to a system. No other system can view this. You can view it from the outside world. It's just associated with that system. And we do that by adding another system parameter of type local. And you can have multiple parameters of exactly the same type. Bevy doesn't care. But these local values that are associated with systems are initialized using the default trait. However, if you do want to create a local variable value with a different value, you've essentially have to wrap your system with a closure. So the closure can look like a system. So closures with system parameters are systems too. So you can essentially have a closure that calls another function which takes your local value as a parameter. In this case, you don't use the local type. It just relies on the fact that the closure will close over the value you defined outside the system. So let me show you a quick example of local storage. So say we wanted to see how many times the move creatures was called. We could add a counter, and then we can just do this. We could, okay. Locals are always mutable, so otherwise, what's the point? And if you run that, you can see counter 1. And if I again put twice, you can see counter 2 right here. Okay. So here's the mental model you want to have. You on the right, you got your schedule, which contains systems, but each system can have their own local storage. Okay, change detection. Change detection, extra queries similar to the with and without that allow you to detect that changes have happened within the world. And that system will only get called if those changes have happened. So, for example, you can detect that you've added components of a type, either by adding that component to an entity or spawning an entity with the actual component. And that can be achieved with the added filter. Similarly, you can detect that a component has changed, either by being accessing it mutably by system or creating a new entity like the added one, and you can use the changed filter. There is removal detection, but this is done through a completely different way. The added and change stuff is done by adding filters to your query. With removal, you have a completely different separate system type called remove components. And essentially the system must be run after a schedule run to actually do the removal of those components, to detect the removal of those components entities. This is why when you do mutate the world and stuff, because it happens to the command list and it happens at the end of a schedule run, you won't be able to detect that until that happens. And so you need another run after that to actually detect that components have been removed. So we could imagine a function called debug players, which detects whether a position has changed. So we want to read the position, and it's a player, and we basically say a player moved to position, but we also want to do it on changed position. And if we add that to our systems, we can see that the player moved to position this and player moved to position that. Okay. Component bundles. Component bundles are just there for convenience, but also for a bit of extra type checking. Usually components are not added to an entity in isolation. As we saw with a player, we added a velocity and a position component and a player component. And sometimes it's just convenient to say, okay, what combination of components represents a type of entity? Component bundles are just simple structs that contain components. That is, all the fields within that struct are components themselves, or they can be component bundles. And they're added exactly like components. The interface is no different. The only difference is that the Rust structs must have the bundle derivation rather than the component derivation. So we can refactor our player here. We can say we derive debug and a bundle, and it's a player bundle. Thank you, Copilot. You come up with exactly the right struct. And we notice that position is a component, that's a component, that's a component. And so we can now go here and change this tuple to a player bundle structure instead. Got it backwards. And we're just passing a normal structure here. So why would you want to do this? This clearly states in the code that these components should belong to each other, and so it's extra type safety. If you want to add a player, you'll get a compiler error if you miss out a component. If you use bundles, but if you just use separate components, you could miss one out by accident, and you could have a bug where something is not acting like a player, and that could be quite difficult to track down. So I would highly recommend using bundles if you can, when it makes sense. Okay, here we go. Nothing's changed. Right, system sets. Sets are a logical collection of systems. They allow ordering and run conditions to multiple systems really easily. We use enums to define the names of the sets. So we can when we refer to a set, we refer to an actual enum. And sets can be nested too. So you can have you can say that you can put a set as well as just a system in another set, and any child sets inherit the parents' sets properties. They're easy to use. We just use the inset method on a system or a tuple of systems. So if you remember, we were doing all these before statements here. We can change this now by saying in here we want to add a system set. So we derive system set here, and my system set show systems. Oh, I want this to be enum. Okay, so we're going to get an error from system set here because system set requires a lot of other ways to be implemented as well. And so now we say, okay, we want all these systems here to be in the set my system set show systems. And then we can just say I want to run before my system set show systems, and we can get rid of all of these. And I think you all agree that's a lot more easier to understand. And if I run that, you can see nothing changed. We just got a much more readable code now. One more concept I want to talk about: run conditions. And run conditions determines if the system runs or not. And all a run condition is another system that returns a bool value. If you return true, that means that the system that this run condition is attached to can run. And we do the attachment using the runIf method. So, for example, I could put a resource in my code saying struct can move and make it a Boolean. Now I add the resource here, and I'm going to say true for now. And I want to create another system. Here's can move, and I will bring in the resource can move, and just return the bool. And essentially, I'm just returning the Boolean from inside it. So this is a very simple system. And then I can do, on the move creatures, I can add runIf can move. So right now we can see that because of the point ones here, we can see that all our creatures and players and monsters, they've moved at the moment. But I can go up to here where insert the resource, and I can just change that to false. And if I look at it again, you can see that none of the creatures have moved, and this is because the move creatures system has never got run at all because of this condition. This is a very, very useful utility to allow you to better control what systems get run and what systems don't get run. Right. There's some more stuff I want to talk about queries. We can combine with, without, and the change detection filters in a logical way. For if you want like an and relationship, we use tuples, and you've already seen that before. I think I've still got it somewhere where I've done a with and change position. So that's an and relationship. For all relationships, you can pass those filters inside a tuple inside the or filter. So example, if I wanted with player or change position, I would just do this. You can query an entity. We get the entity ID for given components. This is as simple as passing in entity as one of the values you want to look at. So for show things, we could type in entity right here, and I can pull out entity and say we just do okay. And here we can see that the entity ID as is printed through the debug thread is there. Also, a very powerful thing is that you can wrap a component in a query with an option type. And that essentially says, I want all the entities with that may or may not have this component. For example, I could wrap an option around player. You can wrap the components mentioned within with and without. You can wrap them inside the tuples that represent the data you want to extract. And essentially what that means is that if that component does not exist, you still get the entity in that query iteration. However, the value will return to be none. If it does exist, it'll be wrapped in the sum state of an option. Some more information about components. Now, components are generally stored in two ways in Bevy. The components can be what's called table-based or sparse set-based. What this effectively means is how components are stored and how they are accessed. Now, the table-based components, which is the default, generally are faster to iterate over. They're placed in memory in such a way that when you run that query and you iterate over it, you get access to those components really, really fast. And so if you've got a large number of entities with same components, this is definitely the best way to go. However, there may be, it is quite valid to add components and remove components at runtime. For example, you could, on a player object, add a damaged component, which then trigger, the existence of which would trigger systems that start reducing the value in your health component over time. And it is quite a valid thing to do that, and your game mechanics could really benefit from being able to add and remove components quickly. Now, table-based components, the way things are stored, if you remove a component or add a component, there has to be a lot of shuffling of where those components are in memory. Now, you can set a component to be sparse-based, and that allows you to be able to add really fast those components. But unfortunately, they are not as fast to access as a table base. So what you gain in the ability to quickly add and remove components, you lose in when you iterate over it in your systems. And as they're useful for mock components that trigger systems, but they don't affect the layout of tables. They don't affect the layout of the of all the components and where they are that are table based. And the way you activate that in your structure, you just add this attribute here. So for example, if I wanted say the velocity to be sparse based, I would just add component storage sparse set here, and that's all I have to do. That means that my system could be able to add the velocity component really quickly and remove them, etc. Also, some advanced usage of systems coming to the end now. Sometimes you don't want systems to. Sometimes you want systems to run only on the main thread. This is usually when systems interact with operating system resources like Windows, or maybe rendering needs to happen on the main thread and so forth. So the way you do that is by adding a non-send or non-send mute parameter instead of res or res mute. If a system has those parameter types, it is flagged to ensuring that those systems are run on the main thread. And instead of adding insert resource, you would add insert non-send resource. So this is useful. It's not something that's common, but for example, the windowing system in Bevy uses this to ensure that its associated systems will run on the main thread. So in summary, the Bevy ECS system is blazingly fast. It is actually one of the fastest ECS systems there is. It's faster than all the other Rust ECS systems according to Bevy themselves. Take that for what it is. It has that speed because it has efficient data storage and automatic multi-threaded scheduling. It is ergonomic. It has a world-class API. You've seen, as I've written code, how easy it is to interact with that ECS. And it's simple to grok, right? You can see the code is very readable. The mental models I've shown you in those diagrams aren't that complicated. And it's quite easy to pick up and reason about as you write more complex systems to implement your game. And so what's next? I want to give a talk about the Bevy app. Now, the Bevy app adds a lot more functionality, which I consider very foundational. It adds plugins and plugin bundles. It has system stages. It has events, system states, and runners. And I also eventually want to start talking about the Bevy engine proper. How do you render? How do you handle assets? How do you do sprites? All that kind of stuff. I'm not really that experienced with the Bevy engine side of things at the moment, so that talk might take a while for me to get around to, because I don't want to give a talk on anything I don't really understand thoroughly. So that is what I plan to do later on. And so I've got it's a quick Q&A session. So does anyone have any questions for me?
Thank you very much, Matt. I do have one question, actually. So you mentioned at the beginning, you referenced Unity Dots and Unreal Mass, I think you said it was called.
Yes.
And you mentioned them as being worse than Bevy. So I was just wondering what exactly makes them worse. Is it that they don't have as flexible API as Bevy, or is it something else?
Unity Dots has some similar features to Bevy. However, in my opinion, I don't think it's as ergonomic. You have to deal with a burst compiler when you have to deal with some special features of C# and the job system to interact with Dots. As you saw with Bevy, it's just functions and structures. You just use normal Rust. It is that simple. And I in my opinion, the API, how you interact with ECS, and the number of concepts are a lot simpler to understand and interact with. So in my personal opinion, I feel that the Bevy's way of doing things is better than Dots. With Unreal Mass, I've used it briefly, and I think it's just awful. Every single component is a whole C++ class. Every single system is a C++ class. They don't even call components, because that interferes with their already established definition of components in the Unreal Engine. They call them fragments. And I just was put off using it straight away. As I said, with Bevy and that kind of API, to me personally, it's just night and day.
Cool. Thank you very much.
Any other questions?
We've got a few messages in the chat, but just lots of thank yous so far.
That's very nice of you.
Hey, thank you very much for the nice talk. Yeah, I just want to ask, what is your impression about like the tooling? Did you have like some debug tools in this other ECS? Do you know about what Bevy offers? Like I can imagine when you come up with this schedules, and in like a really big game, it will get like a bit more. It's getting complex, I guess. So
Yes. You definitely have to manage your systems. Now, Bevy has a layer on top of the ECS system called Bevy app. And usually when you work with the Bevy engine, you interact with that application object. And the application object has very similar API to what you see on the scheduling world. However, the world and the schedule and schedules are hidden inside the app. Now, the app does a lot of high-level features. It has a concept thing called a runner, which will run your schedule multiple times. And it has a concept of stages where it has multiple schedules. So you can group systems into separate groups, and they get executed together. And then when that finishes, the next stage gets executed together, and so on. Bevy takes advantage of that by separating the rendering part from your game simulation part. Personally, I like the ECS way of doing this because usually a feature of a game maps directly to a single system. So, for example, if you want a feature where a poison, for example, I'm just pulling this out of my butt, right? So imagine a feature with something a poison. You literally need to add. All you have to do is add a poison to a entity that also has a health component.
So
and maybe that poison. Yeah, so maybe that poison component will have a rate of damage, right? And so you just create a system called poison entities, which queries on all the entities that have poison and health, and then just does that simple calculation, and it's just there, self-contained, and it's easy. Now there's another system which I didn't talk about called system piping, which allows you to combine chain systems up into an overall system, which allows you to reuse parts, like almost like subsystems. And they're not quite systems, but they allow you to compose together and to create a system. And there's a little bit of reuse there. But that's quite I thought it was quite an advanced topic, and not something I really want to talk about in this talk. Also, mainly because I did most of the slides, I only discovered that feature towards the end, and I want to experiment with a bit more before I want to talk about it. So it's true you're going to get lots of systems, but I personally prefer systems that deal with very small, specific features in a video game than having a monolithic manager which does a lot of stuff, and you'll have spaghetti code and they interact with other managers and so forth. With a system, you can look at it on its own, and you can say it interacts with this data, and that's the only data it cares about. And the automatic parallelism is great. I don't have to think about it. It just happens because of my access patterns. Like a system that reads from a component and writes to a component will never get run at the same time. So I don't have to worry about race conditions. I don't have to worry about using like job tasks and stuff like that, right? Which you often do in this more older way of writing video games.
Yeah, that feels really like stuff getting easier from a programmer perspective. I love it. I
think so. Yeah, I'm sure that there's negatives that people will shout about compared to other ways of writing video games, but I personally quite like it. I like functional structures. I like procedural programming. I don't like object-oriented programming at all. So this suits my personal way of programming quite nicely.
Out of interest, have you found any good rules of thumbs for what's an entity? So, for example, say you had a door, but it had a door handle, and the door handle has its own sort of behavior. You know, you can grab it and move it, but it obviously has a hierarchical relationship to the door. So that kind of maybe like thinking of hierarchical relationships or even associated objects. So I haven't really found like a cast iron guarantee for making, you know, what is an entity yet. But I was just wondering if you had any kind of rules or thumbs or any ideas.
Yes. So you're talking about it's two parts of that, right? That I can talk about. The first part is hierarchicalness. You want a hierarchy kind of relationship in what seems to be a very flat structure, right? You solve that by just having hierarchical components. You have a component that has references to other entities, like a children component, but when you have a feature that interacts, say, deals with a door handle, you don't really care that it's attached to a door. You just care about what components it has, and you deal with those components. An entity is not defined by being an entity. It's defined by what components it has on it and what systems that can affect it. Now, the other half I think is worth talking about is that how do you decide what's in a component? Now, that's kind of like a black art, and I think just dealing with components for a while will help you get a better intuition about what you put in a component, right? For example, I could easily had a movable component and put a position and a velocity inside that component, and then had a system that moves stuff just look for movable component. But in the demo, I decided to separate the position and velocity components out separately, right? That was just a call I made to do that. But you can imagine unmovable objects that still have a position. So for me, it seems like better to separate position away from other coupled relationships, right? So yeah, there's kind of a little black art for designing your components and what's in them. Definitely.
Thanks.
If there are no more questions, I do have a little bit of housekeeping announcements to make for the Rust group. We can come back to questions in a minute
Yours, Alex?
if anyone does have any more.